I'm John McKenzie. One of the most exciting developments in science today concerns the possibility that it may one day be possible to modify and perhaps even control weather and climate. What this could mean in terms of hurricane and flood control and reduction of damage to property, crops, and livestock would be measured in billions of dollars for the United States alone. The value in terms of human welfare for the entire world defies calculation. During the next few minutes, we'll learn what's being done toward altering clouds to increase rain and to decrease hail and lightning. And we'll also look at some of the research aimed at modifying large-scale weather systems, such as cyclones. Dr. Morris Shamus of New York University talks first with Dr. Roscoe R. Braham, professor of meteorology at the University of Chicago.
Dr. Braham, I'm sure that before one can think of modifying a cloud in any way, he must know something of its properties. How do you characterize a cloud?
Well, natural clouds of the atmosphere consist of dense concentrations of very small water droplets, plus perhaps a few ice crystals and snowflakes in the upper, colder regions of the cloud. We can collect these particles by flying through the clouds with an airplane, and if we examine one of these collections through a microscope, we see something similar to that we have in this photograph. Of course, in a natural cloud, the droplets are much farther apart than they are in this photograph. In an ordinary cloud, there would be of the order of 100 droplets per cubic centimeter.
Not very many.
No, that isn't too many. The smaller droplets would have a size of about 5 microns diameter, whereas the larger ones would be about 50 microns diameter. Contrasted with the cloud droplets, raindrops are very much larger. Here is a sketch of the relative size between a raindrop and typical cloud droplets. It takes between 1 million and 10 million cloud droplets to make a raindrop. And the central problem in cloud physics today is to explain how it's possible for so many cloud droplets to come together to form a raindrop.
Well, how is it thought that they combine to form a raindrop?
Meteorologists who study such problems recognize two basic methods or processes by which raindrops are formed. One of these theorizes that the larger cloud droplets, because they are larger and they fall faster, run into some of the smaller cloud droplets, coalesce with them, and gradually build up in size. This process can be modeled in the laboratory, and we've brought along a tape showing the collision between two cloud droplets. A larger drop falls faster and overtakes the smaller drop, coalesces with it. Continued collisions and coalescences with the very much more numerous cloud droplets would ultimately produce a precipitation particle large enough to survive the fall to the ground as a raindrop.
Now, you mentioned there were two processes. What's the other?
That's right. Now, actually, the second process involves another property of water, which we call supercooling.
What do you mean by that?
Well, supercooling is the state of existing in the liquid form at temperatures well below or beyond the normal freezing temperature. Of course, the freezing point of water is 0 centigrade. But water, when subdivided into particles the size of ordinary cloud particles, may be cooled many degrees below 0 centigrade before it freezes. In fact, natural clouds may supercool as much as 20 degrees centigrade, very commonly. Now, the important point is that the saturation vapor pressure over a supercooled water droplet is substantially larger than that of over an ice crystal at the same temperature. Therefore, if in a supercooled cloud one introduces in some fashion a few ice crystals, then the ice crystals will grow at the expense of the water droplets in the manner we have indicated here on our sketch. Here is an ice crystal in a field of supercooled liquid cloud droplets. The droplets are evaporating, becoming smaller. As the vapor moves toward the ice crystal in turn grows in this way. As it grows, it ultimately becomes large enough to fall through the field of cloud droplets. It may run into some of the cloud droplets, which then freeze upon impact, and we have the condition of riming, producing what we call a snow pellet or a Graupel particle.
These are quite different processes then.
Oh yes, these two processes are quite different, but it is this second process which is involved in most modern cloud seeding experiments. Now, we know that this process can be introduced artificially. Well, the rationale of most modern cloud seeding experiments is that clouds can be changed usefully by introducing ice-forming particles.
You can do this in the laboratory.
It can be done in the laboratory. There are two substances which commonly are used for this purpose.
Yeah.
We use dry ice and silver iodide. Dry ice introduces ice crystals because of its intense cold, and this can be demonstrated in the laboratory in the manner that we show in our film clip. Here we see the trail of ice crystals that has resulted from dropping a pellet of dry ice through a supercooled cloud. The ice crystals grow at the expense of the supercooled water droplets. The growing ice crystals get large enough to twinkle the light, and you see them twinkling there on the screen.
Now, why are these particular substances selected for this?
Well, because we can demonstrate their ability to form ice crystals in supercooled clouds, obviously. The dry ice because of its intense cold. Silver iodide because the lattice structure of the silver iodide crystal is very similar to that of ice.
Now, how do you do the silver iodide
Silver
experiment?
iodide is usually released in the form of a fine smoke produced by burning a silver iodide acetone solution in the manner that we show in our film. Here we see a burner mounted on the wing of a light aeroplane. You notice the burner is lit very much in the manner that it would be used in seeding a supercooled cloud.
Now, how do you apply this to an actual cloud?
The most dramatic and obvious case we can see in our picture here. This is one of the early pictures coming from the cloud seeding experiments. We're looking down on the top of a supercooled stratus cloud. We see a racetrack pattern of ice crystals. This pattern of crystals has resulted from flying an airplane around this track, dropping dry ice pellets. Wherever the dry ice fell through the supercooled cloud, it left behind a trail of ice crystals which grew into snowflakes and fell outward through the base of the cloud.
Was much rain produced in this experiment?
No. A supercooled stratus cloud of this form actually contains very little liquid water, so relatively unimportant amounts of snow would fall from it. However, the process itself has great importance. You see that it has cut a hole in the supercooled stratus. In this region, the visibilities are very much higher than they would be in the cloud itself. And this technique has application for, say, opening airports in the wintertime that may be fog-bound by supercooled fog and stratus. In fact, last winter, one of the commercial airlines used such a technique for landing many flights that could not have landed because of supercooled fog.
What is your feeling about these techniques as far as producing actual rain is concerned?
Well, it seems to me that there's considerable evidence that rain can be increased by the proper application of seeding techniques in certain specific cloud conditions. But generally speaking, we still know so little about the matter of cloud seeding that it's we just don't have proof beyond a shadow of doubt that you can increase the rainfall when and where you wish. It's a
Might you
problem.
also be able to decrease it in a cloud that's raining?
Oh, yes, at least theoretically. If one introduced a very large number of ice particles into the cloud, each of the ice crystals may grow to such a slight extent that they would not fall through the cloud base, and we would have what we call overseeding of a cloud.
I see. Thank you very much, Dr. Graham. Now here's John McKenzie.
Meteorologists have learned a great deal about the internal physics of clouds and how rain is created. But clouds can do more than just rain. They can also produce hailstones and lightning, which in turn can produce extensive damage. And it's generally agreed that these are two phenomena we could usually do very well without. Dr. Seamus talks now with Dr. Lewis J. Batten, Professor of Meteorology and Associate Director of the Institute for Atmospheric Physics.
Dr. Batten, we've all heard of so-called thunderstorms. How does the meteorologist characterize a thunderstorm?
Technically, a thunderstorm is any cloud that produces thunder. But usually when we say thunderstorm, we mean a cloud which is called a cumulonimbus cloud, the kind of cloud that grows up as a large white cauliflower, often reaching the base of the stratosphere, spreading out and forming a large anvil. At the ground, it's characterized by gusty winds, heavy rain, and sometimes hailstones.
Is it possible to alter or to modify thunderstorms in any respect?
This is a problem, as you could well imagine, that people have been concerned with for a great many years. In the last 20 years, we've learned something about the structure of thunderstorms, and this has led us to believe that it may be possible to somehow modify them, possibly someday to control them.
Mm-hmm.
The observations that we have in hand have been made mostly with balloons, radar, airplanes, and this allows you to construct a model of the vertical motion of the air in a thunderstorm. Now, one model which has been conceived by various scientists working in this area has conceived a picture such as this one with a strong updraft, essentially vertical, where the air moves from the ground at various other layers, rises at speeds which may reach as high as 60 miles an hour or greater, carrying upward cloud droplets and growing raindrops. Now, in the upper part of the cloud, somewhere in here, above the level where the updraft reaches its maximum, there is accumulated a large concentration of cloud droplets. The liquid water content is very high. Now, if one of the growing water drops on the way up freezes, as it passes through this region of high liquid water content, it collides with the liquid water, continues growing larger and larger, and then may fall to the ground in the form of hail.
Mm-hmm.
Now, this is almost what you would call the traditional model of how a thunderstorm looks. Now, in the last 10 years or so, largely through the work of some people in England, there has been conceived a slightly different picture of the air motion in a thunderstorm. And the important feature of this model is this tilted updraft. It's conceived that the air moves in, up, and moves out in the front of the cloud. Again, the hail starts growing in the same way as it did in the other model. Namely, a large water drop freezes, starts being carried upward in the updraft. Sometimes it falls out in the form of small hail. Other times, the stone falls back down into the updraft and is recycled 2, 3, or 4 times and may, in fact, reach the ground then as large hail. Sometimes the hailstones may reach the size of baseballs. Here's a photograph of a hailstone sent to me by Charles Newman and the U.S. Weather Bureau, which shows such a large stone. You can see it's about 3 inches in diameter.
Now, these two models are not markedly different from one another, I assume. What can be done about modifying hailstorms?
Well, although they don't differ very greatly to the eye, the implications as far as cloud seeding are quite important. The first model, namely the one with the vertical updraft, is the one which has been conceived by various people as being one which would allow you to suppress the form of damaging hail by causing many small hailstones in place of a few large ones.
Mm-hmm.
The second model involves a sequence of events that it appears if you want to modify the hail formation process, you have to overseed the cloud to prevent hail from forming at all. Now, there have been experiments in both directions, here and abroad. Most of the experiments in the United States have involved seeding with silver iodide from the air with modest quantities of silver iodide. And the commercial cloud seeders, some who are engaged in this type of activity, are convinced that they have produced some modifications. But the scientific community is not convinced at this point.
Mm-hmm.
In the Soviet Union, they've been seeding thunderstorms with silver iodide by shooting the silver iodide into the thunderstorms with rockets or artillery pieces. And the Russians, at least some of the Russians, are convinced that they have suppressed the fall of large hailstones. But on various grounds, at this point, one has to be a little skeptical of their conclusions.
In other words, in general, the results are inconclusive.
At this point, one cannot say that it has been positively demonstrated. that large hail can be modified, but there's enough reason for believing that it may be possible to do so.
Now, lightning is also a characteristic of these thunderstorms. How does it come about?
Lightning comes about, again, we believe, as a result of the interaction of the supercooled water and the ice particles in the cloud. The updraft in a thunderstorm carries water droplets and ice crystals of the upper part of the cloud, and their interaction causes the separation of electric charge. And characteristically, in a thunderstorm, the upper part is charged positively, the central portion, just above the 0-degree isotherm, is charged negatively, and occasionally in the rain you find a smaller positive charge. When this charge reaches sufficiently high quantities, you get a discharge to the ground, a huge spark, and we call it lightning.
What's the mechanism for producing the charge? Is that known?
There are various theories. Again, this is a difficult problem because of the difficulty of getting detailed observations. And most people working in this area are of the opinion that you need supercooled water and ice pellets, which interact to separate the charge.
Once you have this charge, what success has there been in modifying such clouds?
Well, again, we use silver iodide. Most of the experiments involved silver iodide in an attempt to eliminate the supercooled water. I mentioned earlier that you need supercooled water and ice pellets to separate the charge. If you can eliminate the supercooled water by overseeding, let's say with silver iodide, then the conditions for charge separation are reduced, and consequently the charge buildup is reduced and lightning should also be reduced. Now, there have been some experiments in this country in various places. The Forest Service is conducting experiments in Montana. We've been conducting experiments at our place in Arizona. And the results at this point can only be said to be inconclusive. Now, this may be because none of the experiments to date have involved the use of so much or enough silver iodide to overseed the cloud.
What about attempts to alter this condition from the ground?
Well, there have been some attempts in recent years, largely through the work of two men called Vonnegut and Moore at A.D. Little, and they have different views on how thunderstorm electricity is produced. They reason that the charging comes about when charged particles from close to the Earth's surface carry up into clouds. They then performed an experiment. They stretched a wire about 9 miles long, 33 feet above the ground, and charged the wire so that it reduced charged particles into the air. These charged particles attached to dust particles were carried into the cloud and were captured by cloud droplets. They made observations with an airplane over the top of the cloud to see whether, in fact, they had produced any changes. And they found that when the wire released negative charge, the cloud was charged negatively. When the wire released positive charge, the cloud was charged positively. So they demonstrated that small cumuli could have their charges modified.
Thank you very much, Dr. Batten. And now here's John McKenzie.
For most of us, weather control implies more than just producing rain or modifying thunderstorms. It suggests man-made control of large-scale weather systems, such as cyclones and hurricanes. Dr. Jerome Spar, Director of Meteorological Research for the U.S. Weather Bureau.
Dr. Spar, Professors Brame and Batten have both discussed the problem of modifying clouds on essentially a local basis and talked something about physical properties involved here. What are the prospects for modifying weather on a wide scale?
Well, it's obviously a long road from cloud modification to large-scale weather control, and we certainly do not have the capability today to control the weather through cloud seeding or any other conceivable technique. After almost 20 years of experimentation and rainmaking operations of various kinds, we're still only on the threshold of this important subject. Large-scale weather systems, as you might imagine, are extremely complex. As shown in this rather complicated-looking picture taken by the TIROS 9 meteorological satellite of the global weather on one day, we can see that the weather pattern consists of a large number of vortices or eddies of cloud and precipitation. It will be obviously extremely difficult to control this complex meteorological system through cloud seeding.
This is the entire globe now.
This is a picture showing the weather on one day
composite.
over the entire globe taken from a meteorological satellite.
What do you mean by large-scale weather?
By large-scale weather, we mean the weather on a scale larger than that of a single cloud. This diagram schematically illustrates the various scales of meteorological phenomena, starting with the small-scale phenomena such as individual clouds. Cumulus clouds, for example, may be about a kilometer or less in diameter. A thunderstorm may be something like 5 or 10 kilometers in diameter. Going up the scale to larger scale systems, we see that such storms as hurricanes or tropical cyclones may be several hundred kilometers in diameter. And when we come to the large cyclones or storms that produce the weather in our latitudes, the so-called extratropical cyclones, these are seen to be of the order of several thousand kilometers. And finally, we end up with the global circulation itself, which is of the order of tens of thousands of kilometers.
Now, is this the region that your colleagues referred to, precipitation region?
The experiments that have been described by Drs. Brame and Batten are experiments on clouds of this scale, weather systems, I should say, on cloud scale. But there have been some attempts to modify the weather on a much larger scale. Two of these have been efforts to increase precipitation over large areas. The so-called rain-making experiments appear to have been most successful in so-called orographic regions, that is, mountainous regions of the world, where nature provides good conditions for cloud seeding operations.
By successful, you mean that rain actually was
By
produced?
successful, we mean that there appears to have been a slight increase in the amount of precipitation over what might have been expected normally.
What about actual storm modification?
There have been two kinds of experiments on storm modification. First of all, there have been some attempts to modify the so-called extratropical cyclones. These experiments have been largely unsuccessful. That is, we haven't been able really, as far as we can tell, to change the circulation in these storms or to change the pressure field or any other characteristic of the storm. One reason for this may be that the natural precipitation efficiency of these cyclones is very high. That is, they produce about as much rain as we can wring out of them anyway. And secondly, the latent heat released by the freezing process and the condensation process does not seem to be an essential element in the development and growth of extratropical cyclones.
And this is the physical basis on which you base these experiments?
The physical basis for any hope of modifying storms through cloud seeding would be the release of latent heat.
Now, I suppose it's true also that you can't detect very small changes.
It's extremely difficult. The noise level or variability of the atmosphere is extremely high, and the influence of the seeding will represent simply a small perturbation superimposed on the natural variability of the atmosphere. So we have to carry out a very long series of carefully controlled experiments and analyze them by statistical techniques.
You mentioned two major kinds of experiments.
The second type of experiment has to do with the hurricane. And the hurricane is a rather interesting target for cloud seeding experiments. It's a relatively small target, as I said before. Its size is of the order of several hundred kilometers. I think I can illustrate it better over here. This is a radar picture showing the appearance of a hurricane on a radar scope. The storm is represented here by these bright areas, which are areas of precipitation. This central region is the eye of the storm, the so-called the calm region of the storm, where there's very little cloudiness. And this is the so-called eye wall, a ring of heavy cloudiness and precipitation in which the winds are very strong. If one were to fly an airplane, as shown on the film which we are about to see, through the wall of the hurricane into the eye, one would see the calm central region, or eye, down below, surrounded by the wall of clouds. And it's in this wall or of the hurricane, the so-called eye wall, that one may find large amounts of supercooled water and possibly be able to produce some modification of the storm structure.
Can you describe the seeding technique that's used?
The technique that is being used or has been used in experiments by the United States Navy and the Weather Bureau so far on two hurricanes, one in 1961 and one in 1963, has been to drop devices which dispense silver iodide through a large volume of clouds into the eye wall. This schematic diagram, which corresponds to the radar picture which we just looked at, shows the central eye region of the hurricane where there are very few clouds, the eye wall surrounding the eye, where we have a heavy concentration of clouds, the spiral bands of precipitation, and here we see the direction of motion of the hurricane. There is a chimney of very tall cumulonimbus clouds in the right forward quadrant of the hurricane, which is shown better in this vertical cross-section through the hurricane. Here we see the chimney of very tall cumulonimbus clouds, which we think contain large amounts of supercooled liquid water. The technique that has been used has been to fly an aircraft over the top of these tall clouds, as shown in the film, and to drop these canisters, which are being loaded on the airplane here, down into the cumulonimbus cloud. As they fall, they dispense silver iodide into the cloud, hopefully converting the water into ice crystals.
In the region that you mentioned.
In the region that we mentioned.
Dr. Sporer, do you see any real prospect for progress in this area?
I think that we have to look forward to a long period of very active and rather expensive research in this field. A very important problem that has to be solved is the relation between the microphysics of the clouds and the dynamics of the large-scale weather systems such as cyclones. And we can only hope to modify large-scale systems if the cloud microphysics plays an important role in the dynamics of the storm. And this has yet to be demonstrated.
Thank you very much, Dr. Sporer. And here's John Mackenzie.
It was shown early and conclusively that man could change clouds under certain conditions. Efforts to extrapolate these effects to larger scale weather control, such as rain-making and hail suppression, have led to widespread controversy. The atmosphere is a difficult medium in which to conduct research, a turbulent and capricious laboratory that frustrates evaluation of experiments. But the stakes are high and well worth the effort. It may be many years before man gains control of the weather, and he may never succeed, but it certainly won't be because he hasn't tried. I'm John Mackenzie. This has been the Science and Engineering Television Journal.
Thank you.